It's my pleasure to introduce Kari Nieminen, who is the owner of KN Manufacturing Solutions. He has a total of 35 years of wire and cable industry experience, gained by also previously working with Nokia Malafer, Pirelli Cables, and Nextrom. His career has included a mixture of commercial and technical hands-on work on machines, controls, and process controls. Kari.
Okay, so my presentation, I'm combining two topics. Actually, the topic is more simple than what we heard. So first, we will discuss continuous gravimetric blending, its benefits, compared to other known systems, better known systems in wire and cable. And on the second part, we will discuss about integration of these systems into lines. Not so much about how to integrate, but why it makes sense to integrate those systems. And a little bit more background to what you heard. KN Manufacturing Solutions, which is my company business, is serving US wire and cable market as a distributor for a Dutch company named Molecular that makes these blending systems there. They are pretty well known in the plastic industry, but on the wire and cable, we have still plenty of work to do. Also, as you heard, like this, I'm doing a lot of control work and represent other companies as well. So that's a quick reason for the topic. Okay, before going, let's look what are those other systems that I will compare to. We have a different kind of blending systems. We have a mountain shape volumetric blender. That means that the mixing is measured with a volumetric measurements or with a volumetric flow rate. And the same thing for gravimetric. The difference is that we are using mass measurements or mass flow measurements. And when we have a batch blender, that means that the batch mix is made in the batches before entering the extruder feeder, maybe in the bucket, in some of the factory, or about to extrude in the oven. There is batch there. And finally, then continuous, which means that all the materials, components of the mixture are fed into extruder same time as a stream continuous flow. And from this, we get actually 4 different systems. We have volumetric batch systems, batch blenders, gravimetric batch blenders, continuous volumetric, continuous gravimetric. And the last one is really the topic I wanted to talk about. Those 3 others are quite well known in wire and cable in the US, but the last one definitely not. And as mentioned, the reason for this topic. So on the next few slides, I try to compare 2 of those systems I described side by side at the time. And I start here having 2 batch blenders. I try to show how they generally work and what are the main benefits comparing to each other. I'm sorry that these sketches are not that great. Okay, here we have on the left we have this is kind of a volumetric batch blender, and here we have a gravimetric batch blender as a graph. Okay, I got a nice picture of this one, but it's just a schematic. So they both have a common. They are sitting on the extruders. They are feeding directly extruders, and they have their own local control systems. And then they have hoppers for main materials and additives. Here. If we focus on a volumetric system, in the volumetric system, all additives and materials are fed using the dosing units, motorized dosing units, into chamber, into vertical chamber or column that acts as a reservoir. It's done in the cycles controlled by some limits in this so the level is cycling around, and if we are getting a good spray, so normally there's a pretty good mixing here on these systems. But units are running same time and with the different outputs that are matching with the mix ratio of the systems. On gravimetric blenders or gravimetric systems, patch blenders, then we don't have a dosing unit. Instead, there are some sort of valves that are metering the material from the hopper to the weighing bin, one material at a time. So and that's called gain in weight measurement. So all the materials, once they are here, when they are measured, they enter to the mixing. The material has to be mixed in order to make it a nice homogeneous product before it can enter into its full. That's so special. Okay, just okay. That's something good with wrong with the alignment. But anyway, just a quick comparison. I guess we can say that on a batch blender is furnished better for more accurate handling of the material variations because they have a load sense. But however, they also have a mixing, and which sometimes at certain conditions and with the certain materials, or sometimes the mixing can make the accuracy worse. So instead of mixing, if the mixing is not good, it can spoil it. However, okay, on the volumetric batch blenders, okay, we can say, and we could see that they are more user friendly, okay, easier, they need less cleaning, and therefore they are they're faster for color changes and that kind of things. However, they will produce some overage waste unless you do something special arrangement. Okay, here now, okay, we have two continuous systems. On the left, we have continuous volumetry. On the right, we have continuous gravimetry. And as you can see, there are not so much difference, and that's really a case. Hardware-wise, they look very similar. So again, they have a material coming from the top. It's feeding through the neck piece to the extruder, and then all the additives are coming. There can be a number of additives you can have, and they're for different materials. And they are coming from the side. Actually, I have a better picture about it. So again, they have a main material is coming through, and the additives are fed then from the side. Here on the picture, we have a dosing cylinder. Sometimes dosing, they are screw overs, but dosing cylinders provide with a better output. You can get a lower rates with these two units. Okay, but if you look very carefully, you can see the difference. Gravimetric system, of course, they must have a load cells, and we have a load cell for the main material, and each units here, they have their own load cell to measure the loss in weight, and which is then from which we can calculate then the total output of the extruder, and then again control the dosing unit to maintain the right mixture. Okay, if we just compare these two, and only difference what we could see was really it's a measurement. One is gravimetric. We have a continuous measurement for the material mixture, so it is way more accurate system than volumetry. And normally the cost difference, this kind of system, I think it's quite minimal comparing the benefits what we can have. One more last one. Let's look at again the two gravimetric systems. This is the same what we had a couple of slides ago, and one we had the last slide. Just to repeat on gravimetric, on the patch system, we measure one material at a time, and one material at a time, and for any errors there are in the measurements or in the control, normally the correction is done on the follow-up cycles. Continuous system, all the materials are measured all the time, same time, continuously. And any error there is, the correction is made as soon as it is detected. We have on a patch blender, we have to have a mixer. The material has to be mixed. There is no mixer here. There's no need for a mixer. Material is fed directly through right here. It's always homogeneous. So that's never an issue. And finally, the design itself. This kind of in the continuous system, we don't have because we don't have any. There's no mix or blend stored anywhere. So we can do very quick batch changes. When the batch finishes, we don't have any overage to clean. Like in the batch blenders, normally there is a materials can be in different locations resulting in that. And it can be either the blend or we can get the bleed off. So that's quickly summarize just to finish the blending part. For closed loop control system, we have a continuous feedback control, no mixing, no material segregation, and we can do very low and high outputs very precisely. So normally the result is very accurate and smooth output on continuous gravimetric. We have there's no blending over it, and we can do color changes, additive changes very quickly, again resulting savings.
Thank you very much.
Okay, that was how to compare. That was first part. Sorry. Then going back now to the integration and start with that part quickly. Before I do that, just to show you how this unit can be communicated with. There are always some kind of systems, analog, digital, this and that. But when I talk about integration, I basically mean field bus integration, Ethernet or something, which basically allows the system then to discuss with the system to discuss read and write with all the information necessary. And why to integrate? As a general term, these systems are coming in the packages. They have a lot of different features. They have a standard features that they must have a standard features that make the machines something that everybody likes them to be. But then they have also some add-on features that may not be suitable for everybody, or people wants to have them different ways. So instead of trying to tweak these systems, we can improve the situation by changing the situation around. So we integrate and we make an adaptation of these systems to the outside world. And then I go through now some very practical reasons why. Okay, the first one is very obvious. We like to have a operational convenience. These systems very often they are in a difficult location, and those operation panels are hard to reach. To having everything in the one console panel or panel where operator is operating everything else, it makes so much sense. And to do that, you really have to do is full integration. You have all displays, alarms, etc. There are a lot of information on this system that we can utilize. There are a lot of process information. We can get like a material output information, etc. that is needed. And with the integration, we can get that. We can log it. We can have it side by side with any other process data there are in these lines. Normally, yeah, it doesn't make sense to keep them somewhere separate. If you integrate it, then it's very easy. Also, we can get the consumption. These systems often they provide information about material consumption, but again, they don't necessarily know what is scrap, what is product, good product, and so on. So once you do the integration, then you can then in your control system to make these differences and define and how they are. You can organize and you can use your own reporting system, whatever you may already have there on the platform. Then there are writing information to the systems. Normally, although these are the systems, they work very well and they detect, but when you have fast changes in a process, you can pass that information to the system as a feed forward to make them respond faster. You can also manipulate how these things behave in a certain conditions. For instance, you can have them tied to recipe systems and etc. Then I go some applications. These are nothing new. All these two applications I'm showing here, they are nothing new. They have been used in wire cable, but again, want to bring it up just because that's how they can be done, and normally they are thought to be kind of difficult applications, but they are not. All kind of dimensional measurements and control. These are typically done, and you have seen this done, master length measurement, kilogram per meter. You have seen this done normally in the long jacketing lines where the diameter measurements are far away and the lines are ramping. So the distance to the measurement has been too long. Okay, those systems they don't need a blender, but now when you have a blender, that system then that capability is there. Once we have generate that kind of measurement, then that allows us to have a dimensional change from master length unit. These are all in the line control PLCs, line controls. They have this information. Once this is integrated, length is always there. Once this is integrated, we have this, and all the dimensional information is there, or it's set there. So we can get any of these OD, wall thickness, layer thickness, ID, depends on whatever application there is. They can be measured, and also they can be controlled. So just the idea that there's a lot of capabilities there, and once you do the integration, when you have that tied, then everything is relatively easy. The information is in one place. Another one also often seen mentioned that was on one slide. Okay, about like a quick color changes, anticipating when we are running. We can anticipate, okay, that we have to change the color at a certain point beforehand, and it can be done. save heat out. Now with the this is done also very often with the volumetric system. I've seen that and have done it myself also many times. But it can also done that way that the system, for instance, calculates. Can calculate when we know how much material there is in the meter of the product. We can calculate. We can do the timing very accurately by itself. So that was my presentation. I hope you found blending interesting, and you found that it's been perfect for many applications. And that's it. Thank you. I don't know how much time I spent.
Well, thank you, Kari. There was a lot of good information there, and we do have a few questions. You indicated on your presentation that continuous gravimetric dosing is more accurate than other forms. Can you tell how accurate that accuracy is?
It's kind of depends. There are factors, but in the normal, the system gets more accurate the longer you run. But what I know that like a 1% from the set point, that's commonly used. So for instance, if you have your dosing set point is 3%, then it's 0.03% of the 3.
Okay.
So.
All right. And what is the difference between using dosing cylinders and screw augers on dosing feeders?
Okay. I think preference, at least the company I represent, preference is dosing cylinders. They produce a smoother output and a wider output. Kind of you can get a lower output and produce a very smooth dosing out. You have a smooth output at a low rate, but still you can go to high output with those proteins. Screw up and you have to do then a compromise.
And finally, can you talk a little bit about the cost advantages of different methods? The case for continuous gravimetric blending at the bottom line. Can you talk a little bit about what the advantages are, just specifically?
Okay, and on gravimetric, okay, it's of course it depends on the process. Most common benefit, I would say, is it's a material savings. They are in a different format, and it all depends on what you're comparing to. But the material savings, of course, because because you can do things with a very little or minimal scrap, and also you can run things very precisely. So like a changeover scrap, you can minimize that almost to minimum. You can okay, if you do a long range length, no changeovers, but then because you are very precise, then you can actually minimize your tolerances, and you can tighten your control. Normally in the blending, I think normally it's so that you have to have enough material there, and so people and they try to overshoot. So tighter control, then more you can save there. But those are the typical. It comes from the material savings there, and then often it leads to other savings.
And finally, it's human nature that people who know how to do something sometimes are reluctant to try something different. How easy is the transition for a company for continuous gravimetric blending?
It should be. These are that's a funny thing, because these are the one of the easiest ways to change and get the improvements. For instance, and that's this. It's a reluctance. That's this correct term. and because you have a batch blender there, you replace, you put the same similar thing, because it depends on who is doing the replacement. And people don't, when people don't think about what other things there are and the difference, then they just want to play safe and easy. But these things are easy to replace and easy to adapt. And I think we are talking about rather than more than hours than days. It's and so and you can get the paybacks very quick.